I'm now going to try and work through most of the problems on the test number 2 practice problem set. These problems are in WebAssign. I actually went ahead and printed out the problems. So for instance, here's problem number 1. Instead of trying to go back and forth, actually what I'll maybe try and do is actually try and work out the problems on this test. I think there were like 30. Now some of these problems are repetitive, so I may not work every single problem. And for instance, on this problem, there are multiple parts. I may not work every part if it's repetitive. And I'll probably work fairly fast. The goal here is not necessary to teach how to do these problems. I've already created the video lectures that you watched that explains how to do these problems, but just to go ahead and do them. So this first problem, find 2 positive coterminal angles and 2 negative coterminal angles. I think I'll probably do just A and B, since C is just like B. So once again, coterminal angles are angles that start and stop in the same place. So for instance, and the way you find coterminal angles is you either add or subtract. Now for degrees, you either add or subtract 360 degrees, because that's one trip all the way around the circle. If you're looking in radians, you add or subtract 2 pi. Now the whole key to having positive coterminal angles is that your final angle has to be a positive number. Doesn't matter how you got that angle. You could have added or subtracted 360 degrees, but as long as the final angle is positive, that's a positive coterminal angle. So for instance, my initial angle is 640 degrees. I need to find 2 positive coterminal angles. And what I'm going to do, I'm going to initially, so here's the positive angles. I'm going to initially subtract 360 degrees. And when I do that, I get 280 degrees. So even though I subtracted 360, maybe you would think that would give me a negative coterminal angle. Since the answer is 280, that is a positive angle. Now, if I subtracted 360 again, I will have a negative coterminal angle. And I will do that in a minute for my negative angle. So now to get another positive angle, since I need 2 of them, I'm going to add 360 degrees. And I think that actually gives me 1,000 degrees. So there's 2 positive coterminal angles. Now for the negative ones, I'm going to pick up where I left off with this 280. I'm going to go ahead and subtract 360 degrees, because then I will have a negative 80 degree. And then if I subtract 360 more, I have negative 440 degrees. Now I do have the answers with me here, so each time I finish a problem, I want to take a quick look, because I don't want to mess up and do the problems incorrectly. So that looks correct. I guess I should have written the answers up here. So these are the answers for the first problem. For 6 pi over 7, so now I have to either add or subtract 2 pi. So for the positive coterminal angle, let's add 2 pi. But of course now, here I have like a fraction. I'm adding a fraction and a number. So really, I'm not going to add 2 pi. I really have to get a common denominator. 2 pi is the same thing as 14 pi over 7. So here you have to do a little bit of work with adding fractions. So then you get 20 pi over 7. And then if you add 2 pi again, so once again, 14 pi over 7, 34 pi over 7. So those would be the two positive coterminal angles. Now to get the negative, I'm just going to subtract 2 pi, which in this case, I'm going to write as 14 pi over 7. So that's negative 8 pi over 7. And then from negative 8 pi over 7, I subtract 14 pi over 7 again, and I get negative 22 pi over 7. So these would be so let me check those. 20 pi over 7, 34, and negative 8, negative 22. So I'm not going to do this last one. The last one, you do the same thing. You would add 2 pi. In this case, it would be 10 pi over 5, and then subtract 2 pi. So once again, the principle of a coterminal angle, say for instance, the problem we did, 640 degrees. There's 360 degrees. And then to get to 6, you know what? I'm not going to take the time. I was going to see if I could do it quickly, but it's not going to be so quick. So all right, I'm going to try and use another pen that maybe doesn't, because these pages have problems on both sides, and if it bleeds through, hopefully we can see this well enough if I use this pen. All right, number 2. Find the exact radian measure of the angle. So here, now here they have 3 parts. They give you 3 angles in degrees, and they basically want you to convert these to an angles in radians. So once again, 3 of the exact same problems. I'm just going to do the first one. So I've got an angle in degrees, and I want to get to radians. So basically, a lot of times I say 130 degrees equals how many radians? So this is where you write down your initial angle. We set up our, what's called our unit fraction. The unit I start with goes in the bottom of the unit fraction. What I'm trying to get to goes into the top. Now, normally you don't write radians, but I'm writing it here just to make it very clear what's going on. Then inside the parentheses, you ask, what's the relationship between degrees and radians? And we, in these problems, normally say that 180 degrees is equal to pi radians. So this is a unit fraction. This thing really equals 1. So we're not changing the actual value of this. We're just changing the units. Because what happens is, so when we multiply, the units on the top cancel with the units on the bottom. The answer is going to be in radians. And now it's 130 times pi over 180. So it looks like this reduces down 130 over 180. I can divide both by 10. And I get 13 over 18 pi. So that should be the answer for part A. Now, a 130 degree angle is the same thing as a 13 pi over 18 angle. Now, problem 3, they flip it around, where they give you an angle in radians, and they want to know what this is in degrees. Now, actually, I don't like these problems because actually all 3 of these angles are like special angles. So these are actually all in the unit circle. So I'm going to go ahead. So I automatically know right now what the answer is for these three, because they're part of the unit circle. These are actually all special angles. But however, just to prove the point, the method, I'm going to take one of these. I'll take this one, 11 pi over 6, and I'm going to convert it to degrees by the method we use if we don't have a special angle. I don't know why in WebAssign they don't choose at least one or two of these to not be a special angle. So in other words, I could write in the answers to these pretty quickly, but I want to show you the method in case you ever have a problem where it's not a special angle. So once again, you do a unit fraction. I'm starting with radians, so radians are now on the bottom, degrees are on the top. I know there's 180 degrees in pi radians. So in this case, the radians cancel out. Actually, the pi's cancel out. So I have 11 over 6 times 180. Now I can sort of do some reducing. I know 180 divided by 6 is like 30. So I already have 30 times 11, which should be 330 degrees. All right. Problem number 4. Express the angle as a decimal to the nearest 10,000th. So actually 4 and 5 are the same. 4 just has degrees minutes. 5 has degrees minutes seconds. So let's do number 5. It's more work, but it has minutes and seconds. So basically, we want to know what is this number going to be written as a decimal and not with. So the idea is it's going to be 237 point something. And the part to the right of the decimal is what I'm converting. 49 minutes, 42 seconds. I need to convert that to a decimal. And it's going to be less than 1 degree. We have to see what it is. So what I do is I start with I'm going to I first take the seconds, and I want to convert 42 seconds into minutes. So I'm going to use my unit fraction again. I'm starting with seconds. Seconds go on the bottom, minutes go on the top. The relationship is there are 60 seconds in 1 minute. But this is the kind of problem where you're going to use your calculator because we're not talking about any kind of exact answers. So basically it's 42 divided by 60, which is 0.7. So 42 seconds equals 0.7 minutes. I'm going to take that 0.7 minutes and then add it to the 49 minutes. So what I really have is, I can say this, 49 minutes, 42 seconds really equals 49.7 minutes. In other words, this 42 seconds is the same as 0.7 minutes. But now I want to take this 49.7 minutes and convert it into degrees. So I start with minutes on the top, minutes, degrees, 60 minutes in 1 degree, 49.7 divided by 60. Let me write down all these digits and we'll see what kind of answer they want. 0.8283. Now they want me to round to the nearest 10,000th of a degree. Wow, I better write some more. So this is tens, hundreds, thousandths, 10,000. So this needs to be the last digit. So I look to the next number to see whether I should leave this as a 3 or bump it up to a 4. Since the next number is a 3, this will just stay as a 3. So then my final answer is 237.8283. And I'm going to look to see, and that is correct, thankfully. Now they sort of flip it around, and they say here is a angle written as a decimal in degrees, and they want to convert it to degrees, minutes, seconds. So once again, I know right away it's going to be 320 degrees. Now the key is the 0.7545, I need to convert that into minutes and seconds. So I'm going to take the 0.7545 degrees. I want to convert that into minutes. So degrees on the top, degrees on the bottom, and minutes. 60 minutes in 1 degree. So 0.7545 times 60 minutes is 45.27. So what I do is I take the whole number part, the 45, and that becomes my minutes. And then I take the 27.27 minutes, and I need to convert into seconds. How many seconds is 0.27 minutes? So I take 0.27 minutes. I want to convert to seconds. Start with minutes, minutes on the bottom, seconds on the top. 60 seconds in 1 minute. So 0.27 times 60, 16.2. And I think they want me to round just to 16. So I think the answer should be 320 minutes, 320 degrees, 45 minutes, 16 seconds. And that is correct. All right, number 7. Now we talk about arc length and looking at, once again, if you have an angle here, theta, the radius is how far from the origin to the end of this line. And then we look the distance you travel when you start here, when you move through this angle, and you have this equation, S equals r theta. But don't forget, the key is if you use this equation, it only works if you put your angle in as a radian. You cannot stick it in as a degree. Now, actually, I think I'm going to skip 7 because there may be a problem. So there's 2 kinds of equations. This is arc length, but also sometimes they'll ask for the area. It almost looks like a triangle, but the bottom is curved. And the equation to find that area is 1/2 r squared theta. Once again, theta is in radians. I think there's a problem where they ask for both of these. So I think I can do both of them. Let me see if I remember correctly. Where am I? Yes, the next problem on these practice problems, problem number 8. There's 2 parts, and they actually make me use both equations in a sense. So here's a 45-degree angle. Here's a picture. They say find the length of the arc of the colored sector if r is 9 centimeters. So we're saying the radius is 9 centimeters. We could also say that this is 9 centimeters here. And here's S, and we need to figure out what S is, the arc length. Well, the equation is S equals R theta. However, I cannot plug in 45 degrees in for theta because 45 degrees, it's in degrees. It needs to be radians. However, this is nice because this is a special angle. If they give you a non-special angle, you may have to do the conversion from degrees into radians. But I actually know that since 45 degrees is my special angles, I know it's pi over 4 radians. So I can say S equals radius 9 centimeters times pi over 4. So this is one, and they say round to 2 decimal places. So I'm going to grab my calculator. And you want to use your pi key on your calculator to get all the precision. So pi times 9 divided by 4 equals 7.0685. So round to 2 decimal places, that's 6. Should it go up to 7 or stay at 6? Well, since I got an 8 here, I'm going to bump it up 7.07. Now the second part says find the area of the sector when r equals 9 centimeters. Same problem, except now they're asking for the area. So the equation for the area is 1/2 r squared theta. So 1/2, the radius is 9. I should have put 9 centimeters here. 1/2 times 9 centimeters squared, and theta, once again, is pi over 4. So once again, grab your calculator. Pi divided by 4 times 81, which is 9 squared, divided by 2. And it says round to 2 decimal places. Here's the actual number, 31.808. That needs to bump up to a 1, right? So 31.81 square centimeters. Just check to make sure I didn't mess up on those. 7.07, 31.81, very good. All right, so those aren't too difficult. The key is you just have to make sure your angle is in radians. All right, let's see what we have next. Number 9. Find the values of the 6 trigonometric functions for the angle theta. Assume A is 5, 12, and 13. So here is a triangle, and they want you to find all the trig functions. Let me redraw this triangle so we can see it easier. So this bottom here is A, which is 5. Obviously this is theta. Hypotenuse is C, which is 13. And this one is B, which is 12. So they've given us the right triangle, and they've given us all 3 sides. So basically it's a matter of knowing the trig functions. So katoa. So sine, opposite over hypotenuse. Opposite is 12. 13 is hypotenuse. The sine is 12 over 13. So ka, adjacent over hypotenuse. This is the adjacent 5. Hypotenuse is 13. 5 over 13. Tangent. Toa. Opposite over adjacent. 12 over 5. Now, I call these sort of the three main trig functions, and these remaining three are the ones that I call are sort of the minor ones. The cosecant sort of gets paired up with the sine. The cosecant is actually the reciprocal of the sine. So if your sine is a fraction, the cosecant, you just flip the fraction. So if the sine of theta is 12/13, the cosecant is 13/12. The cosine and the secant are sort of paired up. If I take the reciprocal of the cosine and flip the top and the bottom, then I get the secant. And cotangent is just reciprocal of the tangent. So if tangent is 12/5, the cotangent is 5/12. And I really don't have to even look because those are so straightforward. All right. Number 10 is another right triangle. Find the exact values of x and y. Assume s equals 5. So this is 5. My angle's 30 degrees. Now the reason I can do this, first of all, exact value means no calculator, no decimals. There might be square roots in your answer. That's what an exact value means. But I can do this because 30 degrees is one of my special angles. So 30 degrees, this side is like the opposite, right? And this is my hypotenuse, and this is my adjacent. If I want to find x, what's the trig function that relates the opposite side to the hypotenuse? It's the sine, right? Sine is opposite over hypotenuse, so I can say the sine 30 degrees equals 5 over, in this case, hypotenuse is called x. So if I do a little algebra, if I solve for x, multiply both sides by x, divide both sides by sine of 30, I have x equals 5 over the sine of 30 degrees. Of course, since this is a special angle, I know this from my unit circle. I know the sine of 30 degrees, if you think of unit circle, right? 30 degrees is right here. The sine is the, I know this right here is square root of 3 over 2, 1/2. The sine is the y value, so it's 5 over 1/2. Now you got to be able to use complex fractions. If you have a fraction in the bottom of a fraction, you simply take the reciprocal, flip these, and multiply the top by that. So that's just going to be 10. So x should be 10. What about y? Y is the adjacent side. Opposite over adjacent. Now here I have a choice. Since I know the hypotenuse is 10, I could also do cosine. I guess I prefer cosine rather than tangent. I'll just do cosine. But you could have done tangent, doesn't matter. Cosine of 30 degrees, so ca, adjacent's y over 10. If I want to solve for y, multiply both sides by 10. 10 times the cosine of 30 degrees. Once again, this is a special angle. I know from my unit circle right here, cosine of 30 is square root of 3 over 2. 10 times square root of 3 over 2. 10 over 2 is 5. Should be 5 square root of 3. All right, not too bad. Number 11. Now actually, I'm going to look ahead because some of these are the same. Maybe I'll choose the hardest one. So you got this one, and then we've got number 12, this one, number 13. Maybe I'll actually do 2 of these. Maybe I'll set them all up, but I might not finish them. And you'll see what I mean by that. So the key is here, they give you one trig function for the angle theta, and they want you to find all the rest of trig functions. Now the key to doing these problems and getting the correct answers, you have to know where this angle is. You know, we've got 4 quadrants, quadrant 1, quadrant 2, quadrant 3, quadrant 4. Whenever you do these kinds of problems, the first thing you have to do is figure out what quadrant your angle is in. Because once again, the quadrant is going to determine whether your final answers are going to be either positive or negative. The key here is they tell us an acute angle. Acute means it's between 0 and 90 degrees. So I know for this problem, theta is in quadrant 1. So when I get ready to get the numbers for all these trig functions, quadrant 1, I know everything's positive. So I know right away, I don't have to really worry about it for this problem. All my answers are going to be positive. The other problems are not that way, but this one is. So what you do is, now you take this trig function. So it's 2 parts. First is figure out where your angle is. The second part is, I like to take the trig function and create a right triangle based upon that trig function. And I do that by saying the sine, so katoa, the sine, so is opposite over hypotenuse. So I could say, I could create a triangle where the opposite side is 5 and the hypotenuse is 13. So let's do it. Opposite, I'll say this is 5, hypotenuse is 13. Because if I say, what's the sine of theta? The sine is 5 over 13. So this triangle sort of represents this trig function. What I'm going to do is now I'm going to use the Pythagorean formula to find the length of this third side. And once I know the 3 sides of the triangle, I can get all my trig functions. Pythagorean formula is going to say you take this hypotenuse and you square it, and I subtract this other leg squared, but I have to take the square root of all of that. This is 169 minus 25, which is 144. Turns out the square root of 144 is 12. So this side of the triangle is 12. Now I just have to apply my definitions of trig functions. Well, they've already given me sine up here. I don't have to do that. I could do it. Cosine, so ka, adjacent over hypotenuse. Toa, tangent, opposite over adjacent. Now, cosecant is just the reciprocal of the sine, so 13 over 5. Secant is a reciprocal of the cosine, 13 over 12. And cotangent is a reciprocal of the tangent, 12/5. Now let's do the next one. Hopefully there's a little bit of a twist. Oh, I'm not going to do it again because once again it's an acute angle. I don't want to do that. All these are acute angles. Very bad. You know what? I might. Let's do this. I'm going to stop here, and I'm going to let's stop this video. I want to add in a better problem for this, so I'll make a change and we'll pick it up here. So let's stop here and we'll pick up again around problem number 12.